All right, so read the problem here with me. Area of a parking lot is 600 square meters. A car requires 6 square meters. A bus requires 30 square meters. The attendant can handle only 60 vehicles. If a car is charged $2.50 and a bus is charged $7.50, how many of each should be accepted to maximize our income? So clearly, this is kind of a business situation, right? Where we're running this business and we're parking vehicles, cars, and buses. And there's all these requirements or stipulations that we have to follow. Okay. We're going to use the information here to set up a system of inequalities, okay, or constraints. We're going to graph them, and then we're going to come up with an objective function that we can use to, in this case, they want us to maximize our income, right? You're in a business setting, you of course want to make as much money as you can, okay? So always start by defining variables. How many of each should be accepted to maximize income? When we say how many of each, what's the word each implying here? Cars and buses. So let's say X equals number of cars, Y equals number of buses. Okay, so then there's several inequalities that we can come up with here based on the given information. So most of these problems, they're real world problems, okay? In the real world, you typically can't have a negative number of something, right? So you can't have negative cars, you can't have negative buses. So right there's enough information to give me two inequalities or two constraints. I can say X is greater than or equal to 0. The number of buses has to be non-negative, or I'm sorry, the number of cars has to be non-negative. And then I could also say Y is greater than or equal to 0. Okay? All right, now I can write a third constraint based on the area of my parking lot and how much space each of these vehicles takes up, right? So it says area of the parking lot is 600 square meters. Car requires 6 square meters. A bus requires 30 square meters. So 6 square meters for every car. That would be an expression to represent the area taken up by all the cars in the lot, right? Add that with 30 square meters for every bus, and that expression all together right there represents the area of the vehicles combined, right? Both cars and buses. That has to be less than or equal to 600. Notice why it's an inequality here. Like, you don't have to use all 600, right? But if we want to maximize income, we probably want to fill up as much of the lot as we can. So we got to come up with this combination, like how many of each type should I, park in order to get the most money possible, okay? All right, so I've used the 600, I've used the 6, I've used the 30. I like crossing numbers off after I use them. The attendant can handle only 60 vehicles. That in itself is enough for one more constraint. What do you think? What would it look like? The attendant can handle only 60 vehicles. Jackie? Very good. X plus Y less than or equal to 60. So we're saying the number of cars added with the number of buses, you can't have more than 60 total. Okay? All right, so cross off the 60, and notice the only numbers that are left are the money values. And those are what we're going to use to make our objective function. Okay? Notice we're trying to maximize income, right? So income implies money. So my objective function here, I'm going to say f of xy equals 2.5x plus 7.5y. $2.50 for every car part, added with $7.50 for every bus part. That's combined going to give me my total income, my z value. Okay. All right, so to me, that's probably the hardest part. If you can't set the constraints up properly, then everything else is gonna, it's gonna be wrong from that point on. So clearly, we got to be able to do that properly. And then the next thing that's challenging is, can you graph it? Because the numbers are bigger here in a real world setting. All right. So notice that inequality of 6x plus 30y less than or equal to 600, that's got some pretty big intercepts. The x-intercept of that is 100. Okay, so I need to account for that in my graph. All right. Now here's what I like to do a lot of times in these real-world situations. I like to take my grid that I've been given and make it entirely the first quadrant. Okay, so to do that, I'm just going to treat this like my y-axis and this like my x-axis. Okay, so now that whole grid's representing quadrant 1 where both x and y are positive values no matter what, right? Okay, so first constraint, x is greater than or equal to 0. That I technically already drew, but I'm going to do it again with a different color. So that would be a vertical line of the y-axis. And for that, I would shade to the right of it. Okay. Y greater than or equal to 0, I technically already have as well. That's the x-axis, and I would shade above it. Okay. Now, before I go any further, let's adjust our scales here. Okay. I'm just going to go by fives. So I'm going to make this 25, this 50, 75, and 100. Same thing here. All right, so 6x plus 30y less than or equal to 600. The x-intercept there is 100. Plot a point. And then how about the y-intercept? 600 divided by 30 is... Say what now? I would say 20, right? Where'd you get? Did you say 5? What? No, I was looking at something else. Okay, all right. So let's plot right there. Okay, so slope is rise over run, right? Rise over run. Rise is y values. Run is x values. So this is going to be 20 over 100. What's that reduced to? 2 over 10, but that's going to reduce then to 1 over 5. So I like reasoning that out because if all I plot is the x and the y intercepts, they're so far apart when I try to draw. If I don't have a ruler, I'm probably not going to draw a very accurate line. And it's very important to be accurate here because we're ultimately going to be looking for intersection points, right? So from that y-intercept, let's go down 1 space and right 5. And just keep doing it until you get to the other point there. Okay, so the shading for that one, if I use the origin as a test point, I would end up with a true statement. I'd have 0 is less than or equal to 600. So right now my overlap between the three constraints I have graphed is this region here, right? Okay, I'm going to clear that for a second because I still have one more to graph. X plus y less than or equal to 60. The x and the y-intercepts there are both 60. And pause, I should have said this. So on the slope for the last one, it's a negative 1/5, isn't it? Okay. All right, so back to 60 and 60. Let's plot those. So right here and right here. And the slope there would be what? Simplified slope for that one. -1. So might seem a little redundant, but an overkill. I'm going to plot several points. So I get a nice straight line. Origin for that would be giving you a true statement as well. So you would shade underneath that one. So when it's all said and done, your feasible region is this one right here. And it has 4 vertices to it. 1, 2, 3, 4. Everybody okay with the graphing? Okay, so to me the hard part's done. So now I make my table of values. XY on the left, f of xy on the right. So my first vertex is the origin, 0, 0. And if you plug that into the objective function, you're just going to get 0 out. So that means if I don't park any cars and I don't park any buses, I don't make any money. Makes sense. Okay. All right, next one, let's go with that point directly above. So that vertex would be at, what are the coordinates of that? Does that appear to be 0, 20, yeah. So park 0 cars, park 20 buses. So that's going to give you 7.5 times 20. So 7 times 20 is 140. Half of that's 10. So that's 150, isn't it? So if you park 20 buses, you get $150 out of it. Okay, then we've got next vertex is at 50, 10, right? Okay, so if I park 50 buses, so 2 times 50 is 100, 5 times, 0.5 times 50, that's 25, so that's 125, plus 75, 200. And then lastly, final vertex is that x-intercept over on the bottom right there, which is 60, 0. Let's see, so 60 times 2.5. I'll take 60 and double it to 120. Half of 60 is 30, so that's going to be a 150. All right, which number do I want? Do I want 150 bucks or do I want 200 bucks? Of course I want 200. I'll take an extra 50 in my pocket. I care about the maximum here, so I'm going to say you can make a maximum of $200 by parking 50 cars and 10 buses. Any questions on that example? Okay, so one more. Read it with me here. Snack bar cooks and sells hamburgers and hot dogs during football games. To stay in business, it must sell at least 10 hamburgers, but cannot cook more than 40. It must also sell at least 30 hot dogs, but cannot cook more than 70. Snack bar cannot cook more than 90 items total. Profit on a hamburger is 33 cents, and on a hot dog is 21 cents. How many of each should the snack bar sell to make a profit? Okay, what do we want to make our variables? Okay, I like X and Y. What do you want to make X, Fuma? Okay, number of hamburgers. Y is number of hot dogs. What's better, a hamburger or a hot dog? Hot dog? Hamburger? I feel like if I go to a football game or a baseball game, I got to have a hot dog. In general, though, I like hamburgers better. Okay, so let's see here. A lot of times you can do the X and Y greater than or equal to 0, because of course you can't have a negative number of hamburgers or hot dogs, but we can be a little more specific this time based on what's given here. It says we have to sell at least 10 hamburgers, but you can't cook more than 40. So we want to sell at least 10, but we're never going to be able to sell more than 40 if we can't cook more than that. So inequality for that, I could do a compound inequality. I could say 10 is less than or equal to X, which is less than or equal to 40. So I use the 10, I use the 40. Now I could do the same for the hot dogs, right? You must sell at least 30 hot dogs, but cannot cook more than 70. So that would be, bless you, 30 is less than or equal to Y, which is less than or equal to 70. Okay, but then I have the stipulation on how much total I can cook between the two. It says I cannot cook more than 90 total items. Who knows why? Maybe you just don't have the time to. Maybe we don't have the staff to. Who knows? Okay, but what would be an inequality for that constraint? Yep, X plus Y less than or equal to 90. Okay, so clearly the numbers are pretty big here again. I think I can get away with my scale being the same as I did on the last problem. I'm going to make the whole grid quadrant 1. And let's go by 5s again. So this is going to be 25, 50, 75, 100, same here. Just in general, the smaller you can make your scales, the better. So what I mean by that is if you can go by 5s instead of going by 10s, go by 5s. Okay? If you can go by 2s instead of by 5s, do that. Okay? The smaller, the better. Okay, so 10 is less than or equal to X, which is less than or equal to 40. What would that look like when I graph that in the coordinate plane? What do you think? Elaborate, be more specific.
So you would have the closed dot at 10 and then the closed dot at 40.
I think you're thinking one dimensionally though. What would I do it in 2 dimensions? Um, right. So the variable here is x. That tells me I'm going to get vertical lines out of this. One at x equals 10 and one at x equals 40. So let's see, right here would be x equals 10. And right here would be x equals 40. And the shading for those two would be in between, right? Okay, so then next set of constraints has a y variable to it. So now we'll get 2 horizontal lines, right, at 30 and 70. And the shading for those would also be in between. So right now the overlap is in this rectangle right here. But then we still have one more constraint to consider. X plus y less than or equal to 90, you've got y-intercepts and x-intercepts of 90, right? So that's going to be here and here. Slope on that is -1, just like on the last problem. So a lot of similarities. Again, I like to fill the grid up here so I get a nice, accurate, straight line. Okay, and the shading for that line, test point of the origin, is going to give you a true statement, so you'd shade underneath of it, right? So when it's all said and done, your shaded region, your feasible region, would be in here. Don't get lazy on me. Please make sure you do the shading. All right, so I've got 5 vertices to this region. Okay. Now, I haven't made my objective function yet. Just like the last problem, we're trying to maximize profit. So profit means money. The only numbers I haven't used yet are the profit values I get for each item, right? So let's do f of xy equals 33 cents per hamburger. So how about 0.33x plus 21 cents per hot dog, so 0.21y. And then let's do our table. Okay, so let's go the bottom left vertex there. That's, let's see, what are the coordinates of that? 10, 30? Let's just write them all out real quick. 10, 30. Then the one on the top left, that would be 10, 70. The one to the right of that, that appears to be at 2070. And then we got one at 4050, it looks like. And then the bottom right one, 4030. All right, so let's just plug those into our objective function. So 0.33 times 10 plus 0.21 times 30. I'm getting $9 and 60 cents. Boy, that's a great profit. Wow. 0.33 times 10 plus 0.21 times 70. I'm getting 18. A little better. 0.33 times 20 plus 0.21 times 70. $21.30. A little better. 0.33 times 40 plus 0.21 times 50. 23.70. 0.33 times 40 plus 0.21 times 30. 19.5. So again, we want to make the most money we can, right? So we're looking at this value. You can make a maximum of $23.70 by selling 40 hamburgers and 50 hot dogs. And notice the combined total there, 40 and 50 is 90, and we have that stipulation we can't make more than 90, right? So it's fitting to make the most money, you need to make as much as you possibly can between the two. All right, any questions on that? So both of those were similar in that we are maximizing profit. Sometimes you're trying to minimize costs, like an operating cost. If you're trying to produce an item, obviously you want to minimize that so that you can then make more money when you go to sell it. Jaden?
What do you actually do to get like
The 23.7 and the 21.3 and all that?
Yeah.
So I'm taking each of the ordered pairs and I'm plugging them in right here for X and for Y.
And where do you get that equation from?
So I came up with that based on, it says the profit on a hamburger is 33 cents and on a hot dog's 21 cents. So the objective function is what you're always trying to maximize or minimize, okay? So if we're saying we want to maximize profit, that tells me I should save the money values to make that objective function. Okay? Any other questions? Okay, so we're going to practice this in that same linear programming practice file. You got a couple word problems in there. Let's see, we have 14 minutes left in class, so you could probably knock one or two of those out right now. And then whatever you don't get finished, just make sure we get that done for Friday. We are done with the unit. Okay, this was the last thing we needed to cover for this unit on systems. So we're looking at a test on Monday. Okay. So on Friday we will of course go over the answers to these. We'll have a review, and then I might even do a little bit of our next unit, which is a unit on matrices. Okay. But then I won't give you any homework on that. Your only homework over the weekend would be just to prepare for the test. Okay?